Okay, so we'll go to the next talk in the program. It will be presented by Dr. Richard Graham remotely. Dr. Richard Graham is Senior Director, HPC Technology at NVIDIA's Networking Business Unit. His primary focus is on HPC network software and hardware capabilities for current and future HPC technologies. Prior to moving to Mellanox NVIDIA, Rich spent 13 years at Los Alamos Lab and also Oak Ridge National Lab in computer science, technical and administrative roles, with a technical focus on communication libraries and application analysis tools. He's a co-founder of the OpenMPI collaboration and was chairman of the MPI 3 standardization efforts. So today you will be talking about offloading collective operations to the BlueField DPU. So Rich, welcome to the program. You can share your slides and then please get started.
Okay, can you hear me now?
Yeah, the slides are coming. The presentation mode you need to make, and might be the volume needs to increase a little bit.
Okay, can you hear me now?
Yeah.
Okay. So I will start. So okay, so as DK said, I'm going to be talking about offloading collective operations to the BlueField. Can you hear me well enough?
Yes.
Okay, so as DK said, I'm going to talk about offloading collective operations to the BlueField data processing unit, or the DPU. Now the focus on the talk today is really on collectives. There are other things you can certainly offload to the DPU, but that's not the purpose of this talk. Why is this not going? Okay. So first, I'll give a bit of introduction to what the BlueField DPU is, so people have an understanding of what it is, and use that in the context of what we do to offload collective operations to this unit. So the BlueField-2 DPU. The BlueField-2 DPU is a system on a chip. BlueField-2 uses the HDR, or the 200 gigabit per second technology, and it's targeted at offloading and accelerating various aspects of application storage, various requirements for the data center. So I've listed here on the left-hand slide some of its characteristics, from a computational perspective. So maximum message rate that the card drives is 215 million messages per second. That's through its ConnectX core, and I'll get to describe what the hardware itself is here in just a moment. It has 8 computational cores. It has a spec int of 70. Memory bandwidth is on the order of 17 gigabytes per second. That's the memory on the ARM, and it can drive NVMe offload at about 10 million IOPS per second at a size of 4 kilobytes, and the NVMe snap can also drive it at 5.4. But the most relevant things here with respect to offloading communication are more the computational specs and the message rates and the like of this device. So talking a bit about the device, there's a cartoon of the device on the lower right hand corner of the slide. So the system on a chip first of all has in it a ConnectX core. So it has all the capabilities that your standard ConnectX card supports, all the offloads, computational characteristics and the like. It also has several ARM cores. In the case of BlueField-2, it's 8 A72 ARM cores. And it has memory attached to it and a single memory controller. And there's also a PCI switch that allows data to go either to the ARM side or to the HCA core, and of course data can flow from the ARM cores into the DPU. There are also several other specific additional acceleration engines on this particular card, but those are really typically targeted at storage and security and the like. So I won't talk about them here. So actually, before I switch slides, just at a high level, I think this is the only slide I have talking about this. There is a software stack associated with using this device. It's called DOCA, so it's a data center on a chip architecture. It provides a variety of interfaces to the network capabilities, whether they're security focused, network focused, storage focused, and acceleration libraries underneath them. And I'm not really going to get into a lot of discussion on DOCA in this particular talk. It also has abilities to support orchestration, managing the card, telemetry, and the like. And so those are services provided for users that are trying to use this device to be able to ease the use of the device. So some of the things, for example, that sit in the acceleration libraries are things like UCX, the point-to-point interface. There's also support for collectives, and I'll talk about that a bit today too. So those are some of the pieces that exist there, just so you get a flavor of what's there. But there are other things certainly that are present there too. So from a philosophy perspective, this is general philosophy, but it's also focused very much. It's also very much a part of what we focus on with respect to how we use it for collectives. Is the notion of how you use this device. So typical servers have, on the host side, they have the application running, but they do a bunch of other management activities also, whether it's infrastructure management, think of your resource allocator or the like. You have software-defined security, software-defined storage, and software-defined networking. So a lot of this communication stack, for example, runs or all the communication stack software side runs typically on the host. So all your collectives, for example, would run on your host in a architecture like that. And the network is a separate unit, right? And of course, we offload things there so that the host and to help make the host more efficient. But with the advent of the accelerator, there's an additional capability or additional capabilities that are added to help make the system overall more efficient. And so first of all, we have the goal is to make as much of the compute resources on the host available for compute, and move as much of the management capabilities or functionality to the DPU, to the degree that it makes sense. There's also a boundary in terms of security that exists between the host and the DPU. So for security type of implementations, this is one of its advantages. And so what's moved to the DPU are things like infrastructure management. A lot of security activity is moved to there. Software-defined storage can be moved to there. And what I'll talk about today in particular are some aspects of the software, collective communication software, as part of the stack that can move down to the DPU. And of course, we have the regular acceleration engines that we have with the ConnectX core, as well as other capabilities that are being added to assist here. So from a taking a different look at this, I have a picture here of how we at NVIDIA look at and implement our support for computation, for a computational stack. So we have, of course, support for advanced computing. You're probably familiar with a lot of these pieces here, the performance aspects, the low overhead data transfer aspects and the like. And so those are sort of listed on the left-hand side of this slide, I'm sorry. And on the right-hand side here, there's a picture of how the functionality is partitioned among various aspects of the host. And so if we look at the darker green component here, these are the pieces that are moved to that are supported by the DPU, the adapter, and the DPU. So we have some hardware pieces that are accelerate communication stacks, things like the small data all-to-all and PI tag matching. But we also have a programmable data path. So we have the DPU. We actually have some other pieces too that are programmable in the data path on the HCA. So I'm going to focus primarily on the capabilities that are enabled on the DPU. So let me switch really quickly and talk a bit about infrastructure. So generally, when you developing collective capabilities is a lot of work. There's a lot of infrastructure you need to develop, a lot of putting that aside, independent of the collective implementations of various algorithms. And so so the discussion today will be in the context of an open source project called UCC, Unified Collective Communication, that we leverage for these offloading the collective operations to the DPU, or using the DPU to help accelerate these collective operations. So everything we're doing is in the context of UCC. So from a software perspective, there are several different pieces of software that NVIDIA supports from a software perspective. So we, whether it's higher level MPI and SHMEM acceleration, whether it's support for the open source UCX point-to-point communication library, or the collective communication library that I talked about, HCall, which is also a separate collective library, which is proprietary, not open source at all. Nickel, with its support for Sharp and the like. And so from a software stack perspective, of course, everything is serving the applications. This is the target. So whether you use MPI, SHMEM, other PGAS languages or the like, that's the top level of the stack, and it sits on top of various communication acceleration libraries such as UCX, UCC, HCall, and Nickel, which again, those are the interface to the hardware. And so what we're going to focus on today is the UCC portion of this software stack. So a bit about about UCC. So it's as I said before, it's an open source collaboration under the UCF Foundation. So another project there that you would be rather familiar with, but not the only other one, is UCX, for example. So this is the parallel of UCX in the context of collectives. So it's intended to support HPC and DLML workloads. So that's really a lot of the focus of in terms of looking at performance, and drives a lot how architecture is designed. It's tunable. You need to be able to use different algorithms under different circumstances, and the like, and so you can certainly do things to tune the library. It aims at low latency, high bandwidth, and high throughput. Sort of obvious things that we need in HPC and machine learning and the like. So the goal here, like any infrastructure like this, is to have a single stack that provides a lot of the services for collectives, so that someone that's wanting to develop a new collective library can focus on a new collective operation, can focus on the algorithm and not so much on all the fairly large amount of work that needs to go in to the supporting infrastructure, so that the overall library is efficient. And of course, it targets, from a hardware perspective, both CPUs and GPUs, and now we're adding support for DPUs. And like any sort of project like this, it's extensible. The intent here, as I said before, is to provide access to infrastructure and let one focus mostly on developing the collective algorithms. An architecture picture, similar to other architecture pictures you've seen in the past for UCC. So again, at the top of the stack, all of this is aimed at driving applications. It's driving certainly several different several different libraries underneath it, or capabilities underneath it. The list here is not exhaustive. So OpenMPI and MPICH are of course supported here. There are versions of OpenSHMEM and UPC that also use this capability. PyTorch and TensorFlow, Legion and Parsec, and Vapid. And as I said, there are other things sitting on top of this. So from an architecture, from a UCC architecture, there are core components that are at the top of the stack. UCC also supports, as I said before, several generic capabilities that everyone uses to be able to use this stack. So you have the ability to describe dependencies. So this is the box on the left-hand side. It says architectural aware and deadline-based task. So you can describe the tasks that you can create a graph to describe the collective operations here. You have to, because this is how the progress engine works. And as I already indicate, there's a hierarchical engine and event-driven engine that helps schedule execution and work execution. On the other side, there are also other pieces that are usable. You have algorithm primitives that can be used. You think of some of your, there are topology supports, so support for using topologies within the network. This is generic capabilities, so you have the ability to discover these and describe them and the like. And you have basic services, like you would expect from any communication libraries. It's things like lists and the like. So again, you don't have to go and invent these pieces. getting more to the core of the library itself. So the library itself is designed from the first place to recognize hierarchies. And so there is support for describing hierarchies. This is the box in the middle called hierarchical CL. You also have, so this is at this high level, I should say also, this is where the algorithms themselves are driven. This is where an MPI algorithm might be different from a SHMEM algorithm because they do have slightly different semantics depending on the collective. You also have very basic interface, sort of single level type of driver to the operation, and you can also add proprietary high level functions, and they sit on top of your, in this case, your collective components. So just like UCX, for example, will have pieces for different shared memory or InfiniBand or other networks. Here you have collective oriented components. So you have something that sits on top of UCX. It's called the UCP TL. So UCP is a level inside of UCX that's hardware agnostic. You have nickel TLs, Sharp TL. So Sharp is the support for in-network reductions supported by InfiniBand. You have shared memory TLs, and you can also add proprietary TLs. So the intent here, if you can tell from the design, this is open source, and the intent is to leverage things, leverage development across the community. But as always, vendors at times want to come in and add pieces that they don't want to share with the rest of the world. And so it's designed to be able to have that sort of support, just like OpenMPI is and UCX and the like. This isn't anything new from that perspective. So these are the software layers that are present in UCC, and then you have the underneath it, they sit on top of a range of hardware level support on top of drivers. So you might have verbs, you might have a UCX driver, nickel, Sharp, shared memory, and the like. And I've added here in purple the new support that we're adding, which is support for the DPU. And so also the two boxes in purple here indicate places where we've made changes in UCC to be able to support the collective offload to the library, collective offload. So both in the UCP TL as well as in the lower level driver. So we've actually added a new driver support. So a few things before I get into a bit more of detail on concepts and how the code flows. I wanted to talk about some of the key concepts behind UCC. So one, UCC again, it abstracts resource description so to make it easy to use, and it provides the infrastructure for supporting collective operations and adding the ability to describe different properties for these operations. So, for example, a collective in UCC, I mean in MPI, collectives in MPI are different from collectives in SHMEM, for example. They make SHMEM has some characteristics that are not present in the definition or in the semantics of MPI collectives, for example. And so these sort of concepts are propagated up, are propagated through the interfaces that UCC provides. From a code perspective, we describe the slide here describes the key pieces through UCC code flow. So first of all, you have the library code initialization. This is typical to everything that comes up. So when you start up your application and want to wire up your collective library, you have a piece that does the UCC, the library initialization. You set up various communication contexts. So this gives you the environment in which communication takes place. So for example, you might have support for at the UCX level. If you're using UCX, you might have here support for your UCX endpoints or other parts of other pieces of UCX. So these are common pieces that would be used by various collective operations, trying to reuse the same underlying infrastructure and not have to initialize things for every new collective operation that's implemented or invoked. You also have support for what's called a team. The team is very much analogous to your MPI communicator or the like. It's just UCX's description of the cooperating elements in a given set of corresponding to an MPI communicator. Then, of course, you have your collective operations that are called repeatedly and at the end library finalization. So UCC explicitly, again, like anything, sets up support to be able to define different teams run using the same communication context. Just like in MPI, you have different communicators that in an implementation perspective typically use the same underlying hardware resources and software resources. So from there are just a few slides here telling a bit more about UCC, encapsulation of resources. There's the you have the UCC init here function that's used to start, to initialize things, in terms of the sort of parameters that are used that the library lets you define. So these parameters can be different for different instantiations, as you can define the thread model, for example, that the collective is using. What sort of collective type you're using, what sort of reductions, what sort of synchronization model you might use in the collective operation. So for some, you may want to synchronize at the beginning, at the end, and at the end. Other ones you may want to be a looser from a synchronization perspective, and let the communication handle that. Again, just for those that are at a very high level interested in this, that you have the init functions and version functions and finalize that let you start and finalize the library and get information about the library itself. So here on the slide on the right-hand side below, you have a structure, the library params that holds some of these characteristics of the particular, the runtime characteristics of the particular team that's being, or the particular instance of UCC that's being used. So a bit about the communication context. So the communication context really encapsulates the resources that the communication library is going to use in this particular instance, as well as expressing the degree of parallelism that you have at the network level. So you may have multiple endpoints for a given host or things like that, and so all this is encapsulated in the communication context. It includes local resources such as the queues that you would use to put data out of the network, receive data from the network, or whatever your communication layer is. You can certainly specify affinity for the resource. And in the current implementation, you can bind it to specific cores, specific sockets, to an accelerator. So all of this is supported in the current instance. So for example, accelerators. So we have the DPU accelerator. There's of course GPUs that are relevant here too. And so you can specify affinity with those properties. So context can be created in a variety of ways. So you can have contexts that are allocated on a per process basis. So for example, a single MPI in principle can have multiple contexts if you initiate multiple versions of the UCC library. So this is different from communicators. This has nothing to do with communicators. This has to do with the resources that the communicators will later use. You can also create contexts that are thread-based, and actually use and have multiple contexts defined in that way. And you can even create contexts on a per task basis. In terms of the sort of resource sharing that one can define here, you can define exclusive resource sharing, where every team has its own resource. So if you want to isolate the resources you use for a particular team, you can do that, or the resources can be shared across teams. So it's really a choice of the implementer as to how they want to do this. And all this is started, but when all this is set up via the UCC, and defined and set up via the UCC context create function. A bit about teams. So teams really are an encapsulation of the group of cooperating endpoints. So the endpoints, as I just said before, they can be processes, they can be threads, they can be tasks. But the team is what encapsulates how collectives, the scope of a collective operation. Very much analogous to an MPI communicator. Properties that are given to a team include things such as a synchronization model. So if you do want some synchronization associated here, it can be either it can be on entry, on exit, both, or actually none of them too, if I believe. So you specify what sort of ordering rules need to be followed by those that are using the team. But what's assumed here, for example, from ordering generally, or one of the things you can define is that collectives need to be always invoked in the same order. So that's true for MPI unless you're using persistent collectives in MPI, and there of course the persistent objects need to be created in order, but then the actual collective operations that are going to be executed can be executed in the order with only one, but they have to have only one in the air. And TensorFlow apparently is also another model where the ordering requirements are different from those of MPI. You can also, the properties also you can specify what sort of data types will use this team. So if you want to, you can customize collective operations for contiguous operations so that you don't have to add the extra support you would have for a general purpose data type engine. Or you can also you can also specify things like strided support, which is useful, for example, in the context of the way OpenSHMEM uses it, or it can even, or you can specify completely general as some sort of non-contiguous data types, which matches the general definition of MPI data types. Again, to instantiate UCC teams, one uses the UCC team create post call. It's a non-blocking call, but only one active instance can be in the air at a time. That's so you get the proper pairing of the various team creation invocations. So this is a collective operation. That's the assumption. So a bit about hierarchical teams. This is nothing new at all. So if you consider endpoints, so there's a figure here of 3 nodes, and each node has 8 endpoints, and within those endpoints you have 2 different sockets. And so if you want, you can treat all those endpoints as flat, or you can build a hierarchy. And here's one form of hierarchy that you could potentially build, where you take at the lowest level you group things based on their socket locality, and so you take one of the endpoints on a given socket, the ones that are marked in green, and create a subgroup with one representative for that subgroup in the next level of the hierarchy. And so you would have, and then you can define each of those, the socket leaders, we'll call them, for each of the sockets to form your second level in the hierarchy. And finally, you can pick one of those from each host to represent your network level of hierarchy. So you would have a team of size 3 at the top level. So you can so this is a three level hierarchy description. It's not required. This is just one possible hierarchy. You can define any hierarchies you want. But the point here is that there's general support within UCC for hierarchy, and the details of the hierarchy are really not important in terms of the general support. In this case, you might set up a hierarchy like this if you're trying to leverage memory locality, for example, in the sockets, and keep socket communication local to a socket as much as you can, and go out to more inter-socket communication at higher levels, and then finally network level activity. So from a collective operation perspective, there are several building blocks within UCC. So you have you can initialize the collective. So you call that once. There are 2 ways. You can just initialize it, or you can and then let the progress engine do all the data transfers, or you can initialize and put data on the wire through the init and post operation. It's a local operation, but everyone in the team is expected to make those calls. You have test to check on status of the operation, whether it's complete or not, and then finalize to end the operation. I talked about the support for completion, and then when you finalize the operation, that's when you would release any sort of special resources you might have set up for the operation. From a collective perspective, you can blocking, persistent, and split phase collectives are supported. So that covers the range of type of collectives that are typically in use today in HPC and ML. And that's sort of a very high level description of UCC, just to get you a flavor to the sort of capabilities that the UCC infrastructure brings to the table. Now, what I wanted to do a bit is switch gears now and start talking about going from the general definition of this is what collectives are, this is what UCC does, talking about some of the concepts and some of the things that that need to be paid attention to when it comes to offloading, to the offloading concept, to the DPU offloading. And so I have a cartoon here that helps describe how the DPU offload is different from your typical model. So, and in a lot of ways, it's no different than your GPU model, where, for example, where you will offload computation to a GPU. Here you're offloading, in this instance, and what I'm talking about now, and the DPUs are not restricted to that at all, but what we're talking about here in the context of collective operations is you would offload part of the work for the DPU, part of the collective work to the DPU. So it was something that would help accelerate the DPU. So generally, you know, in your on-host model, you'll probably, just this is general, there are always going to be exceptions, and you can, you know, it doesn't have to be process-based, it can be thread-based and stuff like that. But those are nuances that I'm not trying to get into now at all. But within a host, you'll have a process that within that context of a process or endpoint, if you like, that is a better definition, potentially. You instantiate the collective operation. So all the management for the collective operation, or a lot of the management for the collective operation, happens within that context on the host. So I'm putting aside things like what happens with Sharp, where you would just start something and the network would have all the management. So your management on the process level is minimal. You know, it's basically posting something and receiving a result. And things in other ways of offloading operations to the network, or full collective operations to the network. So the focus here is, again, even in those cases, you have what happens from a software perspective. All the software runs here within the process. Now, when we have an offload to the DPU, the way I like to think about it is you're extending the space, or the computational engines that can drive this operation into the UCC. So into the DPU. I'm sorry. So you have some of the operation that happens on the still within the process. I mean, that's typically how the operation is started in the first place, and then some of the processing that will be done on the DPU. And so some of the points that need to be taken into account here. So there's a wide range of things you can do here. You can be as creative as you want. You can be as simple as you want. There's a wide range in terms of things you can take into of things you can do with the DPU, how to support collective communication. So I've listed a few points here. People may think of other points too, but the first thing, and the number one thing in my mind, is all of a sudden you have an asynchronous agent here. So you have an agent. So the DPU is attached to the host, right? It's a system on a chip attached, as I've described to you before. There's a PCI. You can go past the PCI bus. And you can go either directly to the HCA or to the ARM side of things, and so you have the ability to be able to drive communication in an asynchronous mode. Another thing to take into account is typically, this is sort of a rule of thumb that I like to use, is typically the number of host cores that the DPU supports is roughly an order of magnitude larger than the number of cores and the number of ARM cores the DPU has. So there's, by definition, work sharing, right? So the factor of 10, you know, that's just, you know, it comes from, you know, DPU. BlueField-2 supports has 8 ARM cores. A lot of, you know, servers today have, you know, 64, 128, or even more cores that can generate traffic on the host, and so you have a smaller number of computational engines supporting the collective on the DPU side of things, and so you need to make sure that when you design your algorithm, you take that into account. right? So you can't assume that the DPU, you'll have a one-to-one mapping. If you're really trying to use the whole system, that you'll have a one-to-one mapping between mapping between the resource on the host and the resource on the DPU. And when I say you will have a one-to-one mapping, right? But it will be a shared resource on the DPU versus on the host side. Each core can work on its own, can generate. So if you have 128 engines on the host, you can generate 128 streams of data to the network in parallel. Another thing to take into account is the BlueField-2 cores are not. They're intended for accelerating certain workflows. They're not a general purpose server. You know, your strong server cores. They're not intended to be a strong compute server. They're intended to support more orchestration type things, although they can be used and are being used for other things too, because they do have compute capability, but they're not your strong server cores. So you need to take that into account too when you're designing your algorithms. So you also have some targeted acceleration engines. The ones that are in there today are targeted more at security and storage, so I'm not going to talk about them in the context of collectives. The host and the DPU obviously need, if they're serving the same collective, they need to be synchronized. So that means you have to figure out a way to sync, to make sure that they're running in lockstep. And at the end of the day, are supporting a single collective operation that will be initiated by an application, and the application needs to know when it finishes. A couple of enhancements in the BlueField that really help in terms of managing and orchestrating moving data in a collective operation. So one thing that the DPU can do is it can initiate work requests on behalf of, or it can initiate network traffic or support network traffic on behalf of data that never hits the DPU. So data that either originates from the host or is targeted to the host. So the DPU does not have to have the data sitting in its memory to be able to post a send or the like. And so some people are familiar with this term. There's this thing called a cross-Gavami memory key. It has to do with the way the PCI support is implemented for InfiniBand. So basically, if you can create these cross-Gavami memory keys that will allow you to post sends, post receives, post atomic operations, or whatever you want on the DPU on behalf of data that's on behalf of memory that's host resident. And so you have here in this cartoon on the bottom right, you will initially define the memory key on the host. The memory region that it describes, I've colored in blue here. That memory key can be executed by a work queue that's sitting on the DPU that's marked in green. And the data that happens, whether it's data that flows from the host to the network or from the network to the host, will flow through the HCA without ever landing in the DPU. So that's one optimization that's possible. There's also another optimization that exists, other support that exists for transferring data between the BlueField and the DPU, which is called the GGA accelerator. So this reduces some of the latency, or eliminates some of the latency of transferring data between the host and the DPU. So a bit now to the offload libraries that we've implemented. So within my group, we've implemented some infrastructure to help us implement collective communication for this library. And this is infrastructure that we can share with people. That's not an issue at all. So a bit about the terms that I use. I think I have another 10 minutes, so let me hurry through this. So obviously we have a set of APIs to support offloading functionality from the main host to the DPU. We have a daemon service running on the DPU so that you can start up your application, your MPI application the way you would through MPI run, and then from the application be able to connect to your accelerated portion of your application running on the DPU. So in this case, this would be UCC. So there's already some service that's running on the DPU supporting UCC, and there's an API that basically lets you say, I want to start using that service, and so you can make changes to the communication library without having to do anything, without the application being aware that that's happening. It has support for both local and remote DPUs, so communication can happen with the local DPU and remote DPU. And we sit on top of the UCX infrastructure, since we no need to reinvent infrastructure that already exists and works, and we can and so there are endpoints that become available for communication through that support. From a offloading library infrastructure perspective, the goal is first of all to provide infrastructure that not just we can use for collectives in this case, but anyone that wants to do something else. It doesn't need to be a communication library. Can use also to instantiate, to get a foothold on the DPU and get things set up, and communication set up, bootstrap, so that the particular implementation can do what it wants to at the algorithmic level. It can provide and instantiate all the resources needed. So there's a generic API that lets you do that. And today we use it in the context of OpenMPI and UCC. And let me just make a comment here. Notice that there's a space in OpenMPI. That's the proper way to write OpenMPI. Another in terms of support. So we have within the context of these of the offloaded support, there are these service processes that run on the DPU. Service process serves local, node local endpoints. A given service process can and does support more than a single endpoint, host-based endpoint. So the intent here is to, again, as I indicated before, there's certainly some in general, there's certainly an oversubscription in terms of the number of endpoints that a given DPU will need to support. And that's reflected in this model here, so that you don't end up having a lot of context switches. If you take a model where you have one thread or process on the DPU per host side endpoint, and end up having a lot of context switches and stuff like that. So that's something that we certainly did not want to do. So there's support for this sort of multiple endpoints being served by a given service process on the DPU. There's support for notifications, so you can build up. You do whatever notification you want to do by the algorithm side, whether it's setting notification from the host to the DPU to say I've started. Here's my characteristics, or whatever is necessary within the context of your implementation. And what also is supported there are some endpoint caches for the cross-Gavami memory keys. So just like UCX supports, the standard UCX has its registration cache to support memory keys and reduce the cost of memory registration. in your host-based, GPU-based type of environments. You also need that support for the cross-Gavami memory key. And it's a bit different though, because there's the cross-Gavami memory key is actually supporting is actually paired with a host side memory key, and so there's some changes that needed to be made to UCX, for example, to support this. Because if you see a cross-Gavami memory key, for example, at the UCX level, and you have a small message, you don't want to all of a sudden start copying data because that's not supported. So those sort of things needed to be added here. And as I indicated before, one of the very specific things that we wanted to support with this infrastructure is using this concept of cross-Gavami memory keys, because we want to minimize the amount of memory that's copied between the host and the DPU, and so we make heavy use of the cross-Gavami memory keys. So here's just a cartoon of what this support looks like. So for each host, we have a corresponding support on the on the DPU side that is offloaded. Today it's offloaded to the daemon, but that may actually change here in the future. Let's see. Do I need to say much here? I guess I might as well go through this. I've talked about some of it already. So the offloading engine. So they're both host side and DPU side support, right? They're coordinated. They're not running. They have to know about each other. Remember, the DPU is there to serve the host side at the end of the day. In general, the design of the library is to support a range of offloading services. So today the support is only for UCC, but that will be generalized. We already have use cases where we need that, where we're accelerating both a collective operation and offloading pieces of the application to the DPU, and so we need to be able to support those in the same infrastructure. Let's see what else is. I think I've talked about most of the rest of these already. The only thing I'll say here is two functions. If you try and use this, there's that you use to start the operation is you basically have an init function and a termination function. The offload engine itself will have a description of you'll provide some description to the obviously at init so that the service will be instantiated in the proper way. So we also have execution contexts, and these execution contexts really correspond at the end of the day to the algorithms that run on the code, or on the DPU. And they give the context in which everything happens. So this is how you keep context of what all DPUs you can talk to. But the rules of how you use those are really algorithm dependent. They're not something that's specified by this infrastructure, because the algorithms may want to have sharing between DPUs that happens in a different way. This also, by the way, supports multiple DPUs too. And we'll say one thing. There's also some pretty good documentation for how to use this. So we're about out of time. Let me skip to one slide on the architecture. just pictorially how this is supported. So there's a communication library, communication library at the high level, in this case, OpenMPI, that's using UCC. And UCC uses the offloading library, and UCC also uses UCX. So this is the host side, and on the DPU side, we have just an offloading library that runs. Again, we use UCX because it's infrastructure that works, no need to reinvent it. And then there's coordination that has to happen between the host and the DPU. There's this whole context setup that's done so that they know how to communicate properly with themselves, between themselves. Let me not talk about this. So I want to end with this slide, just to give you an idea of how one might use this infrastructure. This corresponds to one step, for example, in a data exchange in a collective operation. So if, for example, we're trying to there's a collective operation happening between rank 0 and rank 1. And so in green I've marked what happens, or is marked with on the host side, the rank side, in this case the MPI context. In purple we have marked the shadow part that happens on the DPU. So you might, when the collective operation starts, you might tell the library may decide to tell the DPU that I've started a collective and give it whatever characteristics that are relevant for that particular collective. In this particular collective, for example, we want data from rank 1 to I think the text does not match. Oh, it does. I'm sorry. Data from rank 0 to go between rank 0 and rank 1. So this is long data in this case. So in this case we're trying to do a rendezvous-like protocol, and so the DPU 0, the element the corresponds to rank 0 on the DPU will send a message to the appropriate service process on rank 1, telling it here's where the data is coming from. So it'll give it the memory key that corresponds to the data in the memory of rank 0. So rank 0 will tell rank 1, here's my memory key. Please deliver the data to rank 1. And what will happen with rank 1 is rank 1 the DPU on rank 1 is working on behalf of rank 1, and so it will when it makes the read request, it will use the host side memory key on rank 0 because the data is coming from rank 0. Now, because the entity that's initiating the process is the DPU on rank 1, it will initiate the read request on behalf of rank 1, and so it will need to use the Kraskowami memory key. So when it puts a work request to the network to make that read request, it'll use the Kraskowami memory key that corresponds to the memory location in rank 1, and so it'll just make the read request. The data will go from the host rank 0 to host rank 1, never touches the DPU, but the completion will come to the DPU. The completion for that event will be generated on the DPU side, which will then acknowledge the back to the DPU 0 and etc. And at the end, DPU 0 will tell the host side of rank 0, I'm done. So that's one way to use these capabilities. So I'll quit now. I think a minute to go, and be glad to take any sort of questions. So I cannot hear now.
Can you make, yeah. Rich, thanks a lot. We have some questions for you.
Okay.
Yeah.
Go ahead.
Can you hear me?
Yes.
Yeah. So you mentioned in one of your slides that DPUs can do all-to-all. Hello. Yeah. So DPU have all-to-all engines. So is it available in Connect 7 adapters? And if so, how are they exposed to the user?
Yeah. So the DPU. Yeah. So this is not DPU specific. This is support that's in the ConnectX core. And there's a work request that a new work request that's done that comes with ConnectX 7 that gives you access to that capability. And the size of the data can go up to 128 bytes. Each contributions to the all-to-all go up to 128 bytes.
And regarding the cross GVMI capability, when will it be tentatively released in UCX?
So that's still in development. I'm not quite sure yet when we'll release it. I don't know if it comes. I'm not familiar with the release schedule, so I can't tell you. But it'll be in the next several months. I don't know what to say beyond that because I don't know what the release schedules are.
I have.
Yes.
Can you hear me? Oh, yeah. So you mentioned about GPU support in one of the slides. So will UCC kind of coexist with nickel, or do you plan to phase one of them out?
Yes.
Oh, so it'll coexist. Okay.
It might even already exist today. I don't track exactly the state of UCC, but I believe it may already nickel may already be supported with UCC.
Okay.
Basically, download it and you can see what's supported. I just don't remember the full matrix of support.
Oh, yeah. So I think Rich, then thanks a lot again. I think if people have additional questions, they can all follow up with Rich.